Okay, I know a number of you have an exam halfway across campus right after this class, so I'll try and end a few minutes early so you have a little more time to get over there. So we left off talking about functions and particularly about where R goes to find variables. And I asked you to just look through these examples in advance of class so that you'll have it, at least have the context already in your head. So we were starting to look through different kinds of examples of, depending on where the if you've got a nested set of functions, where the function that's the nested function, where is it defined and where is it called from, and how does that affect where R goes to look for variables. So the simplest case that we've already seen is, okay, suppose you set x equals 3 in the global environment, you define some function f, and then f uses x, but x was not yet defined in that function. So one way to sort of write these things out is to draw these sort of boxes and say, okay, we've got the global environment, we defined x to be 3 there, we defined some f within the global environment, so the enclosing environment for f is the global environment. And then we called f here. So then when it goes to look for x, it says, I can't find x within this environment. Where do I go look next? I go look in the global environment, not because I was called from the global environment, but because the function f was defined in the global environment. So it goes to look for the x there, finds x equals 3, and now, just to be clear about what happens next, it's actually assigning to x squared, but it's doing that now within the environment of the function. So now it's saying, okay, x gets x, whatever I did over there, x squared, I guess. This x is coming from here, but now this is being defined in this frame here. Okay, so any questions about that? Okay, so now if we look at this guy, we've now still got f, but now we're defining f2 within f. Right? So we can think of f2 as now another box nested in here. This is f2. The enclosing environment for f2 is f. The enclosing environment for f is still the global environment. Right? And so our example says do something with just print out x. So what's the sequence of operations that R has to go through as it's trying to figure this out? So it tries to do something with x, can't find it, then what happens? Okay, it looks in f, doesn't find an x there, then it says what's the enclosing environment for f? The global, I'll go look there, oh okay, I found it there, now I can proceed. So it's this series of sequential operations. So if we do that, we see that indeed that does work. It prints out 3, which was the value that was assigned to x in the global environment. Okay, so let's look at this guy. Now I'm saying I'm going to define f. I'm going to define f2 within f. So f, the enclosing environment for f2 is f. But now I set x to be 7 within f, right? So now I'm setting x equals 7 within f. So now if I call f2, and it needs to go look for x, well, it can't find x here, goes to the enclosing environment, but it does see x there, so it should use that one. And indeed, it prints out 7. So this one really illustrates the difference between whether R looks in the enclosing environment or whether it looks in the environment from which the function was called, right? Because now I'm going to define here both f2 and f are defined in the global environment, but I'm going to call f2 from within f and set x to be set x to be 7.
The order we measured in this case, I mean, the x equals 7 is assigned after the function is defined.
Well, the x getting 7, that's a bad indentation, so let's make it a little easier to see here. You mean here?
Yeah.
Oh, sorry. Okay, I thought you were looking at that one. Okay, so are you asking if I switch the order of x gets 7 and f2? So let's see what happens. Anybody have any suspicions about what will happen? Okay, so why do you think 3? Okay, say it again.
X hasn't been defined in F yet.
Okay.
So it'll search one up.
Okay, so when it runs f2, there is no x yet in f. So presumably it'll keep looking up, and it should find the 3 rather than the 7. Yep, indeed. Okay. Any other questions? Okay, so then we were looking at this guy where both f2 and f are defined within the global environment. So our picture now has to change, right? We've got an f, and now we also have an f2. Both of these are defined within the global environment. Do I have anything else going on? Yeah, I define x to be 7 within f. But then I run, so x gets 7, I then am running f2 from within f, assuming that I run f, and then I get to being running f2. f2 is this function that looks for x in here, and I'm looking for x, right? So if the scoping rules were set up differently, if this were a different language, maybe it would go look in f because it was called from f. But because of the way that R is set up, it's looking for x in the enclosing environment. So x is, I believe, still 3 in the global environment. It should go to look there. So if we do this, indeed we see it gives back 3. Okay, so this is a little bit more of a complicated example. So here I'm setting y to be 100. I have this function f, but what this function f does is it defines a variable y. It then defines a new variable g, and then it actually returns that function. Right? So what we're seeing here is a couple of concepts, some of which we've already seen before. This idea that functions are just objects. We can pass them around and manipulate them as if they're objects. So there's nothing wrong with creating a function within f and then passing it out. That's fine. So you can sort of think of this function f as being a function that creates other functions. And so you can, in sort of programming language, you can think of this as a constructor. That it constructs another function that you could then use that other function once it's been constructed. But for our purposes here, the interesting question is what happens with enclosing environments. So I'm going to call f. Presumably what's going to happen is this is going to run through, it's going to create g, and then it's going to return g, and that's going to get assigned to h. So then I could actually take h and run it as a function because that's what kind of object it is. Okay, so any questions about the setup here? Yeah, Michelle.
Is the letter x in that case used as a name for it? Like a function x, and then we're passing in only x and not y?
Oh yeah, this is just sort of sloppy notation on my part. So if you have a function where the body of the function is just one line of code, I can just write the body right there. So this is just the body of the function. If I were being more clear about this, I would have been a little bit more formal, and I would have said, okay, I need a squiggly bracket. Now I've got the body of the function, and now here's the end of the function. Does that address your question?
I guess what I'm asking is if it's going to look for the x that we defined earlier, which is, I guess, 3 or 9 or something.
Well, remember, it's not. Actually, okay, so I think I see where you're going. So this is going to define a function. X is just an argument at this point. So then the question is, when we actually run f, where is it getting x and where is it getting y? So let's actually get to that in a second. Okay, so what's the enclosing environment for G? F, okay, because it's defined within F. So therefore, let's see the course. Okay, so then we know that if F is the enclosing environment for G, and G then, when it goes to look for Y, it's going to look in the environment of F, right? Okay. But when we go ahead and run this function F that constructs G, when F finishes, F is going to finish operating. We're going to get down to here, and F is going to go poof. It's going to disappear, right? Because it's run. The body of the code has been run through. We're done with it. R doesn't need it anymore. But if it just goes poof, what happens then to the enclosing environment for for G, and as a resulting closing environment for H. Right, so all of a sudden there would be a problem, because if we sort of broke this out, we'd have, okay, we had F, we define G within F, the enclosing environment where G goes to look for things is F, but now we're saying, wait a minute, F is just going to disappear because it's gotten executed. And all of a sudden, if that were to happen, G would be sort of left in a quandary. Right? So I suppose there are a couple options for what could happen. Maybe somehow G could then default to just having the global environment as its enclosing environment. Or R could sort of realize this is what's happening and say, wait, don't get rid of the environment for F. Keep that environment for F, keep that environment associated with G so that G knows where to find variables as its enclosing environment. So in this case, what happens is that G, and actually the H, that after we have H when we run through this code and get and do the assignment into H, that environment, the enclosing environment that was that environment of F, still exists and it doesn't disappear. And so the terminology that gets used here is that this variable y will still exist in that environment. Y gets 10. And the language that people sometimes use is that y is bound in the closure of the function h. So h exists. It has this environment that was formerly the environment of f that it's associated with, and any variables that are in that environment are sort of carried along with G, and G can then make use of them. So this, if you end up, there are ways to sort of make use of this kind of functionality in sort of slick sort of ways when you're programming. We're doing it here more just as an example to try and make sure we understand what's happening with these frames and functions. Okay, so to convince you that indeed y equals 10 is still associated with G, we can run h of 3 and see whether we get 3 plus 10 or whether we get 3 plus 100. So we can see where it's actually getting the y from. Okay, so if we look at h, oops, that's not the right h. We can see h is a function, takes x, and it has a body x plus y, so everything that we expect. I could actually do this. So if I can do ls, and I can actually pass it in an environment. So what this is saying is h has this environment associated with it. And if I ask what is in the environment of h, it says, oh, there's a g, which is evidently this function g. I sort of wasn't expecting that. And there's this value y. And so we should be able to, I'm sort of getting ahead of myself in terms of talking about environments, but if we did something like this, this should actually work. Oops. So it looks like this function g, this function h that we have created with this thing that I'm calling this constructor, has in its environment both g, which is that original function that was defined in f, and it has y, which has this value 10. And so when we run through and actually run h of 3, it indeed gives us back 13 because it's getting the 10, because it's evaluating y to be 10, because it's looking in, because it has that y equals 10, out in the global was y is 100, but it's looking and finding that y equals 10. Okay, so somebody, was it you or no? Michelle, I guess, asked the question. Actually, what's your name?
Lisa.
Lisa. Okay. So Michelle asked the question, I think, about x. So what was your question about x, Michelle?
I was wondering, in function x, we give it x a value, and if it was
Wait, in function, which function?
or I'm sorry, 95.6,
Uh-huh.
g function x, and I was wondering
Okay.
But I see we put h of 3, so we gave it that.
Right. So by virtue of defining the function g that then gets copied out and assigned to h, h is now a legitimate function. It has an argument x, and so when it runs, it will then. This actually gets into the next section, which says where does R look for arguments that are passed in. It's going to look for x in wherever it was called from, and h is being called in this case from the global environment, so it's going to look for the x in the global environment.
What are the benefits of looking in different scopes?
Well, I mean, there has to be some sort of rule that says where to look.
Yeah, but don't forget bugs if you don't.
Yeah, I mean, right. You can certainly get bugs if you don't know what R is doing and you expect it to do something differently. I mean, there are advantages. There are.
Is there any reason to not pass an argument into a function?
Say it again.
Is there any reason why we shouldn't pass an argument into a function just that it looks like?
Yeah, I mean, in general, I was saying, I guess last time, that in general we want our functions to take anything that they're going to operate on. We want them to take as input arguments, and then we want them to return an output argument, so that you can just think of it as a self-contained block box. I mean, one case that you might want to not pass an argument in is if you've got some really big object in your global environment or somewhere else, and you don't want to actually have to make a copy of it. So that's one context. Although, as we're going to see, R doesn't always make copies in some cases. I mean, basically, oftentimes it is for sort of fairly lazy programming to write a function where you're using a lot of variables that come from, say, the global environment and expect R to just go look in the global environment. So it is something that in general we would want to avoid. I mean, there do need to be rules, and maybe I should just say what I was going to say next about where to look for things, because suppose the function h was more meaningful than any of these functions we've been playing with, and suppose the function h ran a linear regression, right? Then there have to be rules for R to know where to look for the lm function to go find the lm function. And we don't want to have to pass in absolutely everything that a function needs. We wouldn't want to have to pass in, for example, the lm function into this function h. Other questions? Yeah, that's it.
So if you define x inside G's environment, would it run the x you defined, or would it run the argument that you took?
So it should look, since x is just an argument here, it should, if you say function of, well, let's see, I guess there are different questions that we could ask here. So you're saying if we, okay, say again what your question is?
So if you add a line above x plus y, but like x equals 5 or something, would it run x equals 5, or would it run the argument unit?
Okay, so if this were the case and we then ran h, h of 3, x would get to be defined to be 3 initially. Okay, so it would be setting up x equals 3 based on passing in 3 here, and then you'd get to x gets 5, and that would just overwrite your initial x of 3.
So would it error out if you don't give it the argument then?
It would, because there's no default argument for x. If we had said g equals function of x equals 7 or x equals null or something like that, then it would not error out. But if we didn't give it, if there's an argument there, then it's without a default, then it's going to expect that you give it something. Okay, other questions? So the other thing I was going to mention here, and this sort of relates to some of the questions that were just being asked, is I'm just going to go back to I'm going to go to the PDF here, is we can also ask where things that are defined in the argument list are evaluated. So if I do something like this, I'm setting z and x in the global environment, I have my function f that takes a required argument x, a default argument, a required argument x, an optional argument y that hasn't, I say optional because it has a default, and then it does x plus y. If we do f of z times 5, it's going to go look for z in the environment from which f here is being called from. So it's going to look for the z that's 3 here, which makes sense, because whenever we call a function and we pass in something like z times 5, we expect that the z we're talking about is the z that's in our current environment. But the thing that's a little bit different here is for default arguments, it's actually going to evaluate these in the frame of the function. So when it goes, if we just pass in the first argument x and we don't pass in a y, it's going to, when it gets to here, it's going to say, okay, what's x? X was defined to be z times 5 when I called this function. So z times 5 is going to be 15. And then it's going to look for y. It's going to say, oh, y is defined to be x times 3. It's not evaluating this when the function is first called. It's only going to evaluate this when it tries to evaluate y. And it's actually, if y isn't already defined, it's still basically going to be in the form x times 3, and it's going to look for the x in the frame of the function. So it's going to go look for x is 15, because it got passed in as 3 times 5 is 15. So it should add 15 plus, and then 15 times 3, which is 45. So rather than what it will not do is it will not say, oh, what's y? That should be x times 3. What was x in the calling environment? That's 100. It's not going to do that. It's going to take the x from the frame of the function when it tries to evaluate the y. So we can see this behavior here, that it doesn't give us 60. Whereas if we had actually done, f of z times 5, x times 3, it would have given us the answer where it actually used the x that was defined to be 100. Okay, so any questions before I move on? Yeah, Jimmy.
So like for the second algorithm, like if we don't pass a value to y, say we just define it as a random number, or like just define it as has no relation with x, so it will constitute an error, or
If we define y up here,
yeah,
what do you want to define it to be?
just pick up the number, not related to x.
Okay, a constant or a variable?
Yeah, constant.
Okay, so like that?
Yeah.
Okay, so then it's just going to, if I don't pass in y, then it's just going to treat y as 9.
You keep the function, the original one, but like when you want to get a value, like you change like, because for the last one, it's x times 5 and x times 3. You change the x times 3 to a constant, so what will happen? So it will come with.
Yeah, so if I pass in a constant here, it's going to ignore the default value. If I don't pass in anything here, then it's going to use the 9. Okay, so the next thing I wanted to mention sort of goes back to the question that I think Hovar mentioned, and I was sort of trying to justify what R was doing by allowing us to not pass in arguments. So basically what's going to happen is, suppose we have this situation where we've got sort of nested function calls and it keeps looking for things. It gets to the global environment, and suppose it doesn't find what it's looking for in the global environment. At that point, if R were set up such that it errored out, it could just error out, and it could say, I can't find X, there's a problem. But what R actually does is there's now another set of nested environments that R continues to look in. And the basic reason for doing that is because we need to have some system for R going to find objects from packages that are loaded into our R session. And that goes back to my answer to Hovar's question about how does it know where to go find LM if you call LM within a function? For that matter, how does it know where to find LM if you call it within the global environment? So if you type the command search, it'll actually show you the series of nested environments that it's going to go search through. So suppose that we had called F, and the enclosing environment for F was the global environment. What's basically happening is F, if it looks, say, for a variable X within F and it can't find it, it goes up and it looks in the global environment, which is just your workspace. At that point, where it goes to look next is shown from the function search. So it's first going to look, well, the global environment's already there. That's the first thing. This is just a function of in what order I've loaded packages into my R session. So it happened that the most recent thing I loaded, I think, was this fields package. So it's going to go look for things in what's called the namespace or the environment of the fields package. Then it's going to go look in the maps package and so on and so forth. And so if within f, suppose f were a function, and and somewhere in f it calls the linear model function. The way that it goes and finds lm is it just sort of keeps walking up, and eventually it gets to package stats, which is where lm is defined, and it says, oh, I see an lm here, I'm going to use that lm. And then it goes ahead and runs the regression. If you would use something else down there that was not found in any of these, eventually it'll get down to the last one of these. It'll say, I still can't find that variable, and that's when you get the error message that says x is not found, and it gives you an error. So that's the system by which R is looking for objects, and that's the system by which it is able to find things that are defined in these packages. Dustin?
So this is what will allow you to define built-in functions by yourself, right? Or like to give it its own arguments. Like if you define LM as something, it would use yours instead of the...
Right. So I don't know. I forget if I put that as an example in here. I think maybe I did. And I'll get back to your question in a second. So this search pass is basically the same thing. It's just showing you exactly where on the system the particular package that's gotten loaded is. So let me see if I have that example that basically Dustin is asking about. Yeah, so this I do have an example of that. So suppose so this would be fine. I can run a linear model here. Sorry, I haven't done this proper setup, I guess. Right, okay. So suppose that I define my own LM function here in the global environment. And it does nothing, it just returns null, it doesn't take any arguments. It's just a dummy function. Now, if I try and run LM, it doesn't get all the way up to finding LM in the stats package. It finds LM in the global environment because I defined it there, and it tries to use that LM, and it gives an error. It says unused argument y tilde x because my LM that I defined up there didn't take any arguments. Okay, so it's just basically saying so something has gone wrong here. But there are mechanisms for me still to refer to the actual LM that I'm interested in. I can say stats : this is an operator that just resolves the environment that it's basically a resolution operator. It says, okay, look for the LM function in the stats package, and then this code would actually run. Okay, so you got a question. Remind me your name.
So sorry, you use lazy variation when we define functions.
Yeah, I don't want to get into lazy evaluation quite yet, so I think I'll defer your question for a couple of weeks.
And another question is, this R has a notion of function state nature when we define function. You have to include how many arguments in order to really define. For instance, if I define LM, taking one argument, two arguments, three arguments, will be regarded as different functions?
No, I don't. Yeah, it's not actually considering it to be two different functions. It's that there are two different functions. There's an LM function in the namespace of the stats package, and then as I've done it here, there's going to be an LM function in the global environment. So there are basically two different functions sitting in different places, and based on the rules of where R goes to look for things, it's going to find one of them first and use that. But it's not like in C++ where you could have function overloading, and you've got two different functions that have different kinds of arguments, and depending on what the arguments are that are passed in, it goes and finds the right one. It's not doing that.
So if I happen to define a function within the same scope, then I'm going to override the previous definition.
Well, you're not really overwriting it because you can still get it. It's still there. And if I now do an RM on the LM that I defined just up here, and then I just do LM again, it'll get this one.
No, I mean I override what I have written previously in my scope. So I define the function once, and after several lines I define it again, then I'm going to override.
Yeah, then it's going to disappear. Yeah, when we talk about object-oriented programming, we'll see that there is actually a way to have R call different functions, functions that are specific to different kinds of objects, but we'll talk about that in a little bit. Is there another question back there?
So, when the function is destructed, will all the other functions defined in its scope also destructed, or something leave it as normal?
What do you mean by all the other versions?
All the other functions.
So let me actually do this. So you're saying, okay, we've got this. Okay, so right now if I do LM, it's going to show me the LM from the stats package. You can see that by it says it's in the environment in which it exists is the stats namespace. So this is the actual LM function. If I now create this function LM and I do LM, it just says, oh, it's this dummy function I just created. So is your question when I do this, what gets destroyed?
Yeah.
Okay, so the only thing that's going to get destroyed is just this LM that I just defined. So if I now do LM, you can see now it still refers back to the original stats package one. And in fact, if I tried to do this, presumably this is going to fail because these namespaces of the packages are going to be protected in some way so that I can't go in and destroy things that sort of from a package that was loaded. That's sort of not the error message I was expecting. Oops. Let me out. I don't think this is going to work either. Oh, I might be able to give it an environment. So I wonder if I can if I do LM environment equals, I'm not sure if this is the right syntax, but yeah, I'm not quite. I might be able to. I could probably get this syntax to work, and what should happen at that point is it should give me an error message saying you can't remove an object from one of the packages that's gotten installed. Okay. What this is going to do is this is just a little example of just sort of querying the environment. So I'm going to say, what's the parent environment? So I'm going to assign to X the global environment. I can actually assign that as an actual object. And then I say, what's its parent environment? And then I'm going to do a little while loop that keeps printing out the environment name of the parent environment and setting X to be its parent environment. So I'm basically going to work my way up through these nested environments, and we'll just be able to see that this is actually what is going on. So basically, this says, okay, it looks like there's some RStudio package that was the first one that was enclosed in the global environment, and then there's this nested series of packages that were loaded into RStudio. This is somewhat different than on the PDF, because when I created the PDF, I was running it on my machine on the SCF, and I was not running it through RStudio. But in RStudio, this is the series of enclosing environments. This direction is what I meant by this direction on the board. So that shows us what these different sequential parent or enclosing environments are. And if we did that I could do that with the LM function. I say first X is the environment in which LM resides, and then I could say, okay, what are the sequential series of parent environments for that? And this will show us that first it's looking at the stats package. This is a little bit more detailed than I would get into of sort of why it's saying imports rather than package, but it has to do with sort of how R sets up what functions are available to us from within a package. But then it's first looking within the stats package, then the parent environment for that is something called the base environment, and then the global environment, and then it defaults back to that whole list of packages that we already saw before. So there's some repetition here because there's stats here, and then it appears down here again, and base appears twice. So basically, if you're looking in the environment of a package, you sort of work your way up, you get to the global environment, and then you start working your way up again through all the packages that have been loaded. And this has to do with sort of what the dependencies are of the stats package, that it depends on the base package, and then after that, you end up looking in the global environment. Okay, so let's move on and let's talk about frames and the call stack. So the basic idea here is we've talked about enclosing environments for where one goes to look for where R goes to look for objects, but we can also look and see what the sequence of function calls was and look at what the objects in that sequence of function calls is. So basically, basically what happens is when you're making function calls, R basically keeps track of where you are in that series of function calls via something called the stack. And it's basically like a cafeteria tray. You start pushing things onto the stack, and then when they finish, they get popped off. So we can actually query what the current frame is, the frame of the current function. We can then ask what are the frames from which, what are the functions from which that was called, and what are the frames associated with those functions. So if we do that, there are a bunch of these functions that allow us to do this sort of querying. So let's just actually run this and see what happens. So I can ask, what's the number of the current frame? It just says it's 0. And then I'm going to define this function that says, okay, it's going to print out some stuff. It's going to say I'm in F, and my frame number is the result is whatever I get back from sys.endFrame. That's going to tell me the frame number. And if I do sys.parents, that's going to tell me the frame number of the parent from which my function was called. So basically, when you're running a series of nested functions, Arjun is just going to assign a number to each of those. And I can find out what the name of the environment that's associated with that frame number by passing the frame number into this sys.frame function. And similarly, I can find out the name associated with the parent frame with the frame from which it was called in this context by calling parent.frame. And I can use negative numbers to refer to basically relative positions. So some of this takes just sort of playing around with and getting used to it. Okay, so what this does when I run it, it says, okay, the current frame number is just 1, and the parent of that is 0. And it says the frame of the function f from this line, it says, oh, it's this environment that has this base 16 name to it. And it says the parent frame is the actual global environment, because that's where I called it from. And if I try and go 2 frames up, going 1 frame up gets to the global environment. Going 2 frames up, in this context, we're not talking about enclosing environments anymore. We're talking about function frames and what functions are being called. There is no other function that is being called, that has been called. So it says there aren't that many frames. I can't go up that many. In contrast, if now I'm going to call, let's see, now I'm going to call f from within f2. So it's going to print out some information about f2, and then it's going to call f, and f has all those print statements that give information about the frames relative to f. So if I do this, and now I call f2, well, the first thing that happens with f2 is it gives me the information about f2 that I have here. So it says, okay, the frame has this, the name of the frame is this base 16, and then the parent frame is the global environment. And now I call f, and f says, oh, now the frame number is 2, and the parent of that is 1, because f got called from within f2. So 2 is referring to f, 1 is referring to f2, and 0 is referring to the global environment. And it says, okay, the environment of f is this base 16 number, and the parent environment of f is this, which you'll notice is the same as this one, which was the one for f2. So it's basically, now we're talking about environments in terms of the frame, in terms of the call stack instead of in terms of enclosing environments. So now it is where things called from. And that's why we see, okay, f was called from within f2, so it's the parent frame in terms of the call stack is indeed, the parent frame for f is indeed this f2 one. And we could sort of take this to extremes of calling many functions nested within each other. So this is basically just going to be a function that sets up a series of a number of nested function calls. So this function g is going to find another function gg, and depending on what I pass into it, it's just going to recursively call g again. So when I pass in g of 3, g of 3 gets called, then since y is 3, it's bigger than 0, it's going to call g of 2. Then it's going to call g of 1. Then it's going to call g of 0. And at that point, y will be 0, and it's going to call gg. So now I've built up a series where I'm calling gg multiple times. Then I'm calling g multiple times. Then I'm calling gg. And when I call gg, it's then going to print out the result of whatever the sys.status gives me. And what sys.status does is it's going to print out a whole slew of information on the whole series of function calls and what their frame numbers are and what their environments are. So if we do that, we can just see that indeed it's going to sort of print out a whole bunch of information. So it tells us what the calls were. It says, okay, you called g of 3, then that called g of y minus 1, that called another g of y minus 1, it called another g of y minus 1, that called gg, and then sys.status got called. So you can sort of see what the series of function calls is. And then in terms of the numbers of the frames, it says what are the parents of each of those calls. And those are 0, 1, 2, 3, 4, 5. And then it says what the actual hexadecimal base 16 names of the different environments are. So if you need to sort of get a sense of, if you've got sort of a very intricate set of function calls, then you could query things in this way and get a sense of what's going on there. Okay, so are there any questions about that? You'll have a little bit of chance to practice this on one of the problems on the problem set. Okay, so let me just say a few things about strings, and then we'll really pick up with regular expressions on Monday. So I'm going to skip over sections 6 and 7, and we're going to spend a bunch of time looking at section 8, which is about text manipulation. Okay, so basically what we're going to be talking about is how do we go about manipulating character strings in R. And by a character string, I mean any sequence of characters. So that could include a space, could include a comma, could include letters, numbers, special characters. It can include a new line as part of the character string as well. So things like new lines and tabs are also part of strings that we might be dealing with. So I'm thinking of sort of anything that's enclosed in double quotes, and that include all of these different kinds of characters. So in general, if we're working in R, we're going to store those things as actual vectors of characters. So I could have I could have A be a character vector, and it could have a string, ABC, and then a tab, and then a new line, and then a period, and then whatever else. And this would be a legitimate string, and then I could have something more normal. The fire was hot. Okay, so I can print it out. All that stuff is just just enclosed in this character variable. I can print it out such that it sort of evaluates the tabs and the new lines by doing cat. And then it'll actually print it out where it actually interprets that, well, you can't really see the tab here, but there was a tab printed out, then a new line, and then it prints out the rest of this. Okay, so before we get into regular expressions, we have a number of sort of basic functions for manipulating strings. So we can paste together individual strings with the paste function, and I can tell it what to use as a separator when I do the pasting together. And if I already have a character vector, then I can, so this is pasting things together where I give a series of individual arguments separated by commas. I can also paste things together when they're already in the form of a character vector by using this collapse function. So both of those will allow me to create this character string, my name is Chris. Either one of those would work for that. And then basically the reverse of pasting things together is if I did string split, where I give it the string that I want to split apart. This could be a character vector, in which case it's going to work on this in a vectorized way. So it could split apart multiple different character strings. And I say, okay, split based on spaces. So the result of doing that is my, and then name, and then is, and then Chris, because it's split apart based on the spaces. But you'll notice that there's this double bracket 1 in here, which is indicating that it's actually, the result of this is actually a list. And the reason it has to be a list is because if I had given it if out actually were a character vector with 2 items in it, it would be splitting both of those based on spaces. One of them might be, say, 4 or 5 long, and the other might be some other length long based on how many spaces there are. So the result has to be a list because I'm getting back sort of a heterogeneous result, depending on how many spaces that were in each of the strings that were in this character vector out in this case. If we actually want to know not how long a vector is, but how many characters there are in a string, we can use the nchar function. And we can actually split things. We can actually extract sub-pieces of an individual string by using substrings. So this is saying take this, extract the second through the third characters of each of the strings. There are no second and third characters here. The second and third ones here are C and A. Second and third ones here are O and H. So I'm realizing it is a few minutes before 10, and I promised you guys that I would end early so you could get, those of you going to your exam could go. So I will finish here and we'll pick up there on Monday. Thank you.